Hi there. In this section, we're going to start Chapter 4. This isn't actually part of Chapter 4 proper, but it belongs with the material we're going to be covering in Chapter 4. It's actually Appendix E. It's at the end of the textbook or the ebook, and it doesn't have a lot of the visualizations that we've seen for some of the other sections, but it's actually an algebra concept, but because it comes up so much in calculus, it's worth taking a lecture day and covering an algebra concept that some of you have seen and some of you haven't. So if you've seen this before, it's not too bad. It's a lot of algebra, and in the examples in the PowerPoints, I sort of intentionally don't fill in the algebra steps. Number one, it just takes too long. This is going to be one of the longer videos. And number two, it's something you need to practice anyway. So there's two reasons why I don't go over a lot of the algebra. Some of it I do, but not all. So without further ado, let's jump right in. So the idea here is that we're using what's called sigma notation. And this is a giant capital letter, sigma, Greek letter sigma. And the idea is that all of these a's, so a sub m plus 1, all the way up to an, these are real numbers. Just any numbers, doesn't matter what they are. And there's a finite number of them as it stands. So you just start counting at m. So m is like the starting value, n is the ending value. So and I is the index. So the way it works is we say we're going to sum the ai's or a sub i's from I equals m to n. And what happens is then you start at m and you replace I with m. So you just get a sub m. Then you kind of travel this way, and then you put a sum, you put a plus sign in. Then as you keep traveling up from m to n, you hit every number along the way. So if m is 3 and n is 10, you'd hit a sub 3, a sub 4, all the way up a sub 9, a sub 10. So these are just indices. So these a's can be any number. They can be given by a formula. They could be just a random assortment of numbers. Doesn't matter. What we're going to see is mostly formula-based stuff because we're going to be using sigma notation for calculus. So here's a couple examples. I'll just go through these real quick. Just kind of look how it's set up. Again, most of you have seen this, but just in case you haven't, that's why I'm going over it. So look at the index of summation. So we'll start here with this first one. I equals 1 to 4. So it's the summation of I squared from I equals 1 to 4. So we start at 1, plug in 1 for I, so you get 1 squared. Then we kind of travel up from 1 to 4 and put in plus signs in. So we put a plus sign in. On the way from 1 to 4, the next number we hit is 2, so we get 2 squared. So that goes next. And then we keep traveling up, then 3, then 4, putting plus signs in. And this here is a function of I. And it tells us what to plug in. So this is a sort of short, finite sum that's countable, right? You can put this in a calculator and get 30 or whatever. Let's look at part B. So here we go from I equals 3 to n. So this top limit is just a variable. So this entire thing is a function of n. So if you change n, it changes the value of the entire sum. So we might be able to write this in a more compact form, like a formula, and we'll see some of those later, but we might not be able to. And so the idea with summation notation is it takes very large things when expanded. So if n were 100, you'd write 97 numbers out in this sequence, so we really don't want to get into that. This is just a more compact way to write it. Next up, you can see that instead of I, we're using j. Usually I, j, and k are the main ones used, but we'll probably use I for most of them. So here we have 2 to the 0, right? So we start with 2 to the 0, then plus, so we go all the way from 0 to 5. 2 to the 0 plus, 2 to the 1 plus. Just keep going all the way, 2 to the 4, 2 to the 5. Add it all up, you get 63. And the rest of those down here kind of, look similar to that. And the pattern, you can kind of see how it works. So go through the other ones and kind of check it out. Then what I want to show you is down here for f. This one's a little bit different. So all of these contain the index, I, j, k, I. This one doesn't have an I, j, or k. So the index is I. So what's going on here? Well, it's still a function of I. Just like the line y equals 2 is a horizontal line, but that's still a function of x, right? But just any x you plug in, you get a y coordinate of 2. This is really the same thing. So these are all functions of I, functions of j, functions of k. Whereas here, it's just a constant. So we're just summing the constant 2 4 times. 1, 2, 3, 4. So you get 4 times 2. So we'll watch for all that stuff. You'll see how it goes as we get into it. So this is sort of what a bit of your homework looks like. So here we have to kind of go the other direction. So I just want to point out something, that there's no unique way to write summations. Because that index can be set to any value on the bottom, it should be 0 or above. Then there's really no unique way to write this. So what you want to do is just look for patterns. So if we go back, we can see that part A here sort of looks like part C here, right? Because 2 to the 0 is 1, so this is 1 plus 2 plus 4 plus 8 plus 16 plus 32. So it's going to look like this somewhat. Right, so this is going to be, these are all 5 to some power, right? This is 5 to the 0, 5 to the first, 5 squared, 5 to the third, and so on. But what if we wanted to start this at I equals 1? So what we would have to do is this would have to be 5 to the I, right? 5, so 5 to the first is here. So what we'd have to do is actually make it I minus 1. So I just wanted to show you that there's, watch for it on the homework. The homework will tell you what to do. But I just wanted to show you that there's multiple ways of doing this. I could have written this as I equals 0 to 5 and made this 5 to the I and got the same answer. But you can check it, right? Plug in 1. 1 minus 1 is 0. 5 to the 0 is 1. For the next term, I equals 2. 2 minus 1 is 1. 5 to the first is 5. And so it checks. So really, if you're not sure if it works or not, just check the first couple terms and then check the last term. And if all 3 of those check out, you're going to be fine. All right, what about part B here? Well, they all have an 8, so there's definitely going to be an 8 in it somewhere. These are all x to some power, right? So this is x to the 0 here. Just x to the 0 is 1, unless x is 0, and we just ignore that case for now, because it's a single point and actually doesn't change the arithmetic of everything. So, and then we notice that there's this alternating negative, right? It goes positive, negative, positive, negative. So that's represented by this negative 1 here. For the nth term, it's negative 1 to the n. So what we want to do here is we want to start so that the first term is positive, right? So that means negative 1 to a number has to be a positive number. So we don't want to start at 1 for our summation, because negative 1 to the first is negative. So we want to start at either 2 or 0. You're allowed to start wherever you want. Let's just go ahead and start at 0. So here I use j's just to show you how it works. And here we're going from j equals 0 to n. And this way everything checks out. Remember, the first couple terms and the last term should line up. So if you plug in 0, negative 1 to the 0 is 1. 8 stays 8. So right now we have just 1 times 8, so it's 8. X to the 0 is 1, so our first term should be 8. It is. Let's check the second term. J equals 1 is our second term. Negative 1 to the first is negative 1 times 8 x to the first. So it should be negative 8x. It is. Let's check the last term, n. So negative 1 to the n, 8x to the n, and it is. So we're not going to be doing a ton of this sort of stuff. I just wanted to show you some examples so you can see how it works. For those of you moving on to Calc 2 someday, you will do a lot of this stuff in Calc 2. About a quarter of the class is just sums and things like this. All right, let's look at some properties now. So we're going to move forward and just do some problem solving. So if c is a constant, then, so we have these three rules. They're properties of summations, and we're going to use these to do some proofs later and do some homework problems, right? These are properties we're allowed to use. I'm not going to prove these just because the only reason I'm not proving them, it's already a very long lecture. And I'm trying to keep all my videos under 40 minutes. So we'll see how that goes. So if you guys doubt the truth of these theorems, or this theorem and the next one, even though I am going to prove part of the next one, look this stuff up. It's in the textbook, because you have to be able to use these things to move forward. So it's like a special kind of algebra, right? It's algebra with sums. So how do we interpret these things? This is saying the sum of a constant times your terms, that you can pull the constant out. That should be clear, right? This one says I can distribute the summation inside addition. And property B, it's property B. Property C says I can distribute the sum inside subtraction. So that's it, right? And we're going to use these three to get a lot of work done. Here's another theorem. So these are the summation formulas. I'm going to prove A, C, and D later. You are responsible for all three of those proofs. So let's go through it and see what's going on here. So the sum of 1 n times is n. So 1 plus 1 plus 1 plus 1, n times gives you n. So if I add up 1 3 times, 1 plus 1 plus 1, does that equal 3? Of course it does. So this one's not too bad. This one is just this, but we're using this constant rule. And we're just saying, hey, we can pull the constant out. So if you pull the constant out front, you can push the sum next to, if you pull the constant out here, you just have constant times 1, and then you use this. The c is out front, so it's just c times n, or nc. Doesn't matter. Order doesn't matter with multiplication. What about this one? So this one's harder to see why it's true. Some of you might know some proofs about this one. There's also other ways to prove this. If you guys have seen mathematical induction, you can use induction to prove C, D, and E here. I'm not teaching mathematical induction in this class, so if you know how to prove it with induction, and I put on a test, you're allowed to use induction on a test. It isn't considered a valid form of proof. So we're just summing the I. So 1 plus 2 plus 3 plus blah, 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 plus n minus 1 plus n is n times n plus 1 over 2. That's interesting. So all the things on here, just memorize them. I mean, obviously you're allowed to use these as notes, but you still should memorize them. It's going to make the work a lot quicker. And here's another one we have to prove. The sum of the I squareds, 1 plus 4 plus 9 plus 16, all the way up to n squared, is actually given by this interesting formula. That's kind of weird looking. And last one, the sum of the I cubed is actually just this thing squared, which is pretty interesting also. All right, so what we're going to do, we're not going to prove these yet, but I want to use a couple of these I'm going to use a couple of these properties and a couple of these properties to solve a problem. So the problem we're going to solve here is example 2, and just look at it, right? Sum from I equals 1 to n of I times quantity 4i squared minus 3. And so you just think, how can I solve this? So you go back and look at the properties. So this, you can only use these properties, these formulas, if this exact thing shows up. We don't have that exact thing. We do have a sum of the i's, but we don't have a rule about multiplication, right? We can't distribute sums inside multiplication. You can distribute sums inside addition and subtraction and multiplication by a constant, but not times 2 i's. We just don't know how to do it. But we can distribute first. So that's the first thing we're going to do. Okay, so we're just going to distribute this I inside both of these terms. Now you look at this and you say, can I use some of the properties that we saw on the previous slides to get it in the form of constant times a sum And that sum should be an I cubed, an I squared, an I, something like that. Well, we have a rule that says I can distribute sums inside subtraction. So you'd push this thing inside here. So you'd have two of them. And then you can push it inside the constants. And so you'd get this. So this is A and C. I use C first and then A, but it doesn't matter. Anytime you use the summation properties, you can just all use them all at the same time. You just take the sum and push it right up next to 1 I squared, or I cubed. Just push it right up against it. Right? Because sums distribute through addition, subtraction, and constant multiples. Now, we have two things that look like what we have on the previous slide. Even though I haven't proven these formulas yet, we're just going to use them first so we see what they're about, because the proofs are actually really long. Well, I can replace this with, let's go back, with this. And I can replace the other one with that. So that's what I'm going to do. So whenever I see this, I plug in this. Whenever I see this, I plug in that. So let's see what that looks like. Now, I'm going to leave the algebra up to you guys. In fact, if you're not sure if you can do the algebra, pause the video and make sure you can get this answer. It is a lot of algebra. It's not a ton, but it's enough that if I go over all these algebra steps, it's another 20 minutes on the video. And that's your answer at the bottom. So look, this is a formula that's a function of n. So if n is like, 5, the sum of this from 1 to 5 is just whatever 5 is plugged into here. So this is called a closed form. It's a formula that you can use to solve summations. Anytime a summation is able to be broken down in this form, where it's constants plus or minus a summation times 1 I squared, or I cubed, those are the ones we're going to cover. There's a lot more in the real world. These are just the ones we're going to cover. That you will be able to get a closed form answer. And you always want to simplify these. So even though this is technically true at this point, these should be simplified, because the idea is, can we learn something from this formula, basically? And then later on, we're going to do even more stuff to these formulas. All right, well, that's it for example 2. Make sure you can do the algebra. If you haven't verified, it's going to be on a test. On this exam, you'll probably have to do several of these, so make sure you can do the algebra. All right, next one is what's called a telescoping sum. So let's just look at this guy. So it's the sum from I equals 3 to 99 of this thing. So you can just start plugging numbers in, right? So we plug in 3, so we get 1/3 minus 1 over 3 plus 1, so that's 1/3 minus 1/4. And you just keep plugging numbers in. Next one is you plug in 4. So we get 1/4 minus 1/5, and you plug in 5, 1/5 minus 1/6. All the way up to 98, right? 1 over 98 minus 1 over 99. And then last one, 99, 1 over 99 minus 1 over 100. So this thing has 97 terms. And you don't want to write out 97 terms. The purpose of this thing is not to just add this up. It's to find a shortcut way to sum this. And if you look, you can see that those 1/4 cancel here. Because here we have a negative 1/4, here we have a positive 1/4. And once you drop the parentheses, you can just add or subtract those in any order you want. Well, every term in the middle gets canceled, because after that negative 1/5, there's a positive 1/5 in the next term, so it cancels. All the way up to 98, 99 cancels, and so you're left with just 1/3 minus 1 over 100, which is 97 over 300. On a test, I want this as an exact value. Decimals are not allowed for these. So, not too bad. It's called a telescoping sum. You have a couple of these on the homework, and there's one of these in one of the proofs I'm going to do later. So what we have here is sigma notation, but there's limits tacked onto it. So we have a sum and a limit. So what we're doing here is really sort of like a calculus version of an algebra concept, right? So what does this even mean? Well, we're going to learn in 4.1 and 4.2 what this means. For now, it's just an abstract representation of a sum of some numbers. So the first thing we want to do, we saw this before, is we really don't know what to do here. So the first thing I'm going to do is distribute this 3n inside. So, and then I distributed this square. So it's I squared over n squared, and then you bring a 3 over n, gives you 3i squared over n cubed plus 3 over n. The reason I distributed first, again, from an algebra standpoint, you guys are allowed to solve this in any order you want. Because you might be thinking, well, why don't we pull this 3 over n? It's a constant in terms of like being a function of I. There's no I here, so I can pull this thing to the front. Notice I dropped the limit off, right? We'll deal with the limits later. I'm just reducing the algebra on this. You could pull this 3 over n out, but then you run into the problem of now I'm distributing two things, and I'd rather just do the distributive property first, and then I'll split these sums into two. So again, using those summation properties, I have a plus sign inside the summation so I can distribute this summation to both. Then I just keep pushing the summation in until it's right next to a 1, an I squared, or an I cubed. So in example 2, we had an I and an I cubed. In this one, we have a 1 and an I squared. And notice what I did here. This is a 3 over n. We don't have a formula for the sum of 3 over n, but 3 over n is a constant as far as this sum is concerned. So I can pull it to the front. And same thing here. We have a 3 over n cubed. Just pull it to the front. That's what these properties are for, to use them. Now I have formulas for these two guys. So you just replace them with their formulas. Now the algebra on this one gets a little kooky, and I want to show you kind of like a strategy how to solve something like this. So I'm showing you a little bit of the algebra here. Okay, so first step, cancel everything that'll cancel. Okay, this n and this n will cancel, so it's gone. This 3 and this 6 will cancel to a 2 in a denominator. This n and this n cubed, they do cancel if you want them to, but I'm leaving it in just because I want to show you sort of a more general strategy that works. Now I foiled the top, right? Distributed everything, right? And I need to add this 3, so I need to get a common denominator. Okay, so multiply top and bottom by n cubed. I know that looks weird. It was like we had 3n over n, and then I canceled it. What I'm trying to illustrate here is that as you're going through the problem, you don't know what's going to happen. So pick a technique that works in all situations. If you look back later and go, oh, I could have saved some time by doing such and such, that's fine. I'm just showing you a technique that always works. Now what I'm going to do is we're going to add this together. So we're going to get 2n cubed plus 6n cubed. We're going to get 8n cubed plus 3n cubed plus n. Then I'm going to push the n cubed up as a denominator in all those terms, right? So 8n cubed over 2n cubed is 4. 3n squared over 2n cubed is 3/2 times 1 over n. It's 3 over 2n, but again, I want to factor out those constants, right? So again, not showing every step of algebra. This is just a strategy. And here we have n over 2n cubed. So that 1/2 is going to get pulled out front. Then n over n cubed becomes 1 over n squared. Now we plug everything back into the limit. So this is our original limit. Algebraically, this expression is equal. So we just plug everywhere we see this whole big thing, we plug in this whole big thing. So we already did the algebra. I recommend taking everything out of the limit. I really do. Just first of all, it's less stuff to write. So can't go wrong there. Now we use the properties, push everything all the way in. But here we're using limit properties. Remember, we have limit laws. So when the limits exist, I'm allowed to do this. You're allowed to push all the limits all the way in. So here we have the limit of 4. We have 3 halves times the limit of 1 over n, and 1 half times the limit of 1 over n squared. We had a theorem earlier that tells us that this is 0 and this is 0. Right? So the limit of this is just 4. This is 3 halves times 0. This is 1 half times 0. So we just get 4. So the answer to this thing is 4. Might not be real exciting, but that's the way this stuff goes. So I showed a lot of work on this problem. You guys won't have to show this much work, but because there's so much algebra on this problem, I did want to show a little bit more on this one. If you decide there's a better way to do it, feel free. Let me show you one thing you can do. Some of you might have noticed this. Some of you might have noticed over here that if you cancel these n's and then FOIL this out, you get a 2n squared over 2n squared, which would be 1. And you can leave this 3 alone, and you'd get 1 plus 3, which is 4. Hey, that's fine if you want to do it that way. But again, while you're working through the problem, you really don't know what's going to happen. So you might want to play it safe. Keep everything nice and together. So yeah, this is sort of what we do in the beginning of Chapter 4. More stuff like this. Now let's prove some of these formulas. So we're going to prove A, B, and C. We already talked about the proof for A. It's pretty easy, right? If I'm just summing up the number 1 n times, that's clearly just n. For this one, we're going to use a tactic where we name this sequence, this sum, we name it, and then we do some algebra. So here we're summing up the i's, 1 plus 2, all the way up to n minus 1 to m. So we don't know what the sum is. Remember, we're trying to prove that the sum is that formula, right? We're trying to prove that it's this. So I can't just use that in the proof. I have to come up with another way of obtaining that. But we do know that it equals this sum, whatever that happens to be. We call it S. So what we do is we write S forward and backward and stack it on top of each other. So here's S. I mean, it's a little stretched out, but it's the same thing. And then here's S with just all the terms flipped. And what you do is you just add down. So S plus S is 2S. 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. And it turns out that every term along the way, so the first 2 terms and the last 2 terms are n plus 1, it's certainly believable that all the ones in the middle. Because these get smaller by 1 each time, these get bigger by 1 each time. That's why we flipped it around. So they have to sum to the same thing when you add it down. So 2s is n of these, n plus 1 times n, or sorry, n plus 1 plus n plus 1. So this whole thing is n times n plus 1, and you divide by 2, and you get the sum that you were looking for. So great proof. I think it's easier than other proofs of this that I've seen. So this is the one you want to know. All right, next one. So this is the big boy. So what we have here is the sum of the I squareds, right? 1 plus 4 plus 9 plus n minus 1 squared plus n squared. So we're going to call this guy S again, not the same S as before. It's a new problem. And then what we're going to do is come up with a technique for finding that value using algebra. So I'm going to build a new summation. I'm going to call it T because it's a telescoping sum. So right now, it doesn't look like this thing has anything to do with this. It doesn't. It just has enough algebra properties that we can fiddle with it and get S. That's the only reason I'm picking this thing. So first thing we do here is we telescope this guy all the way out. So you plug in 1. So you get 1 plus 1 is 2 cubed minus 1 cubed. Then you travel up. Then 2. So 2 plus 1 is 3 cubed minus 2 cubed. And so on and so forth all the way down the line. Well, you can see that this is telescoping, right? Notice those 2's cancel. All the middle terms will cancel. So only the lowest index term and the highest index term is going to stick around. All those middle terms cancel, the n cubes cancel, and so we're just left with n plus 1 cubed minus 1 cubed. Well, I can expand that. I can simplify that, right? Use your properties of algebra, and you get t equals n cubed plus 3n squared plus 3n. So notice that this is just t in terms of n. Is there something I can do to this to get t in terms of s? Because then I can set that equal and solve for s, and that's what we're going to do. So now we're going to compute t a different way. So it's still the same telescoping sum, but we're going to compute it using a different technique. What we're going to do is distribute first. Again, or foiling, whatever you call it, expand this thing all the way out, like the opposite of simplifying, okay? Right, so, 1 cubed plus 3i squared plus 3i. There's a formula for this, or you can just write it out. Again, I'm not showing basic level algebra stuff. Minus I cubed. So I've switched the order. These are all plus signs. It doesn't matter if you switch the order or not. I just wanted to see what was going to cancel. So I get an I cubed minus I cubed. So look, everything, the cubed parts cancel. Now I'm left with these I squareds. And now it looks like something we did in an earlier problem. Use your properties and push the sum all the way in so that it's up next to the 1, the I, and the I squared. We just proved what this equals. We just proved what this equals. We're trying to prove what this equals. But we do know that this sum is called S. We did that on the previous slide. So you replace everything with formulas. Again, we don't know this formula, but we do know it's called S. So I proved that this guy equals n. I proved that this guy equals n times n plus 1 over 2. And this one, I just called it s a couple minutes ago. So then I simplified it. So we have t equals 3s plus 3 halves n squared plus 5 halves n. So what have I done? Well, I have two different expressions for t. One of them is just n's. The other one has s's and n's. So we have t equal to two different quantities. Anytime you're trying to eliminate a variable, remember, we're not interested in what t is, even though we could find it. Instead, we're going to set these things equal to each other and solve for s. So when you have two things equal to the same number, you can set them equal. Right? So I just set them equal to each other and solve for s. I'm not showing the algebra on this one. That one's up to you guys. And once you do it, you do in fact get what we are trying to show, that the sum is in fact that formula. So, pretty good proof. If you guys know how to do it with induction, you're allowed to do that if I put this on an exam. So that's it for the exercises. If you guys have any questions, you can post on the discussion forum or email me. Not a lot of extra help stuff for this appendix problem, but there are some exercises in the book that you might want to try. And that's it for today. So I'll see you guys next video. And until then, have a good day. Bye-bye.